Okay, good afternoon, everyone, and welcome to the Washington Laboratories Academy webinar series. We do hope you find the next hour or so useful and informative as we've developed our webinar series to deal with some of the technical and administrative issues that our customers face on a day-to-day basis. We recognize that engineering challenges can be complex, and we're always looking for ways to support the technology industry. So some quick housekeeping. I hope everyone can see the title slide on their computer. Please let me know in the chat if you do not. Please note that a recording of this presentation will be sent to all attendees. During the presentation, feel free to send your questions as they arise to the host using the chat window. We estimate that this presentation will take about 30 to 45 minutes, leaving some time at the end for Dr. Archambault to address any questions you may have about today's subject matter. In the event that we don't get to your question or you think of one afterward, you may forward those questions or comments related to this topic to questions@wll.com. And now I'd like to introduce our presenter, Dr. Bruce Archambault. He is an IEEE Fellow, an IBM Distinguished Engineer Emeritus, and an adjunct professor at Missouri University of Science and Technology. He received his BSEE degree from the University of New Hampshire in 1977 and his MSEE degree from Northeastern University in 1981. He received his PhD from the University of New Hampshire in 1997. His doctoral research was in the area of computational electromagnetics applied to real-world EMC problems. He has taught numerous seminars on EMC and signal integrity across the United States and the world, including the past 15 years at Oxford University. Dr. Archambault has authored or co-authored a number of papers in computational electromagnetics, mostly applied to real-world EMC applications. He is a member of the board of directors for the IEEE EMC Society and a past board of directors member for the Applied Computational Electromagnetics Society. He has served as a past IEEE EMCS Distinguished Lecturer, EMCS TAC Chair, and Associate Editor for the IEEE Transactions on Electromagnetic Compatibility. He is the author of the book PCB Design for Real-World EMI Control and the lead author of the book titled EMI-EMC Computational Modeling Handbook. So without further ado, let's get started and turn our attention toward what I wished I knew before buying EMC simulation software. Welcome, Dr. Archambault. It's all yours. You can take it away.
Thank you. Let me share my screen here. Okay, welcome everyone. Now that she's done reading my bio, we're running out of time. And so are there any questions?
That's it.
I'm just kidding. I've been doing simulation for about 30 years. And when I first started, there were very few tools available. Now there's quite a few tools available. And some of them are really whiz-bang. They have great graphics and allow you to see things that you wouldn't normally be able to see. So why do modeling? Well, being safe costs money, and reducing costs usually increases the risk. But as an engineer, design engineer, we need to reduce the costs, reduce the time to market, and manage the risk. And I think simulation also eliminates voodoo magic. I've sat in many different design meetings with other EMC engineers, and they just tell me that, or they tell the designers that you got to do this because I say so, and they don't have any kind of proof that it's going to work, and they can basically be ignored because they have no credibility. And oftentimes there's no other way to get the job done. That means that at very high frequencies, we can't use the low frequency knowledge of, for example, a dipole antenna. Dipole antenna becomes resonant at a half wavelength. Well, once we get up into the 30 gigahertz range, the half wavelength is pretty small. And so all of our products are much bigger than that. And so we're not going to be able to use something simple like that. There's lots and lots of different softwares out there. I know I don't have them all here. I've got probably the most popular ones. But the point is that there's lots of different tools that you can use depending on your budget and depending on what you're trying to do. Each tool is based on some modeling technique. And the modeling technique basically solves Maxwell's equations. And the way they do it varies. And that means the ability of the tool to model everything is impossible. Some tools are really good at long wires. Some tools are really bad with long wires. Some tools are good with shielding. Some tools are bad with shielding. So we're going to go through and talk about some of the different modeling techniques here in a moment. So this is just an example of some models, and the key here is that you have to make sure that you're modeling what you're measuring. There was an example that I was involved with some years ago where I had a circuit board and they wanted to model the power bus. So the middle upper picture here kind of shows what was simulated. And it turned out that it wasn't anything like what was measured. Well, it turned out that there actually was a long wire attached to drive the boards, and the long wire went down to a connector in the floor, the metal floor of the shielded room. But we were working at high frequencies, and currents could be on that wire, and in fact dominated the simulation. So you have to be careful what you actually do. So modeling is here now, and I think that if you go to the symposium, the EMC Symposium, you'll find multiple sessions on just modeling, as well as problems that have been solved by using modeling. But they can't do everything. The CAD file has too much information to be able to model everything. So you can't just download a mechanical CAD file and an electrical CAD file and hit the button and say, go model. You have to break it down into what problem you're really trying to solve. And the old saying about garbage in gives you garbage out applies to simulations like it applies to most things. So you have to be very careful in what you're simulating. But modeling can do some things. It can illuminate using out-of-context equations. It can help you update rules of thumb. It's particularly good at looking at a design feature and doing a what-if analysis. What if I make this longer? What if I move it to here? What if I make the holes in the shield larger, but the metal thicker? All those kinds of things can be solved. And basically, the individual problems can be combined to find the overall result. But as I said earlier, there's no one modeling technique that'll do everything. And so remember what the vendor's goal is. The vendor's primary goal is not to solve your problem, it's to sell software. So you have to be careful with what they claim or what they don't say. And that's why I think it's important to understand how the simulation tools work. So there's a variety of modeling techniques. I'll talk a little bit about quasi-static tools that just do inductance, capacitance, and resistance extraction. But I'm going to focus mostly on full wave techniques. And I put magic in here because I actually had a vendor once, when I asked them how their software worked, tell me that it was proprietary and they couldn't tell me. Well, Maxwell's equations are not proprietary. And as far as I'm concerned, if they can't tell me how it works, I won't know when it doesn't work. And so I have no patience for anybody who won't tell me how the software works. So quasi-static models are typically for very small elements, usually a 20th of a wavelength. It helps you make a lumped circuit approximation. And as I said earlier, it's good for LRC extraction. Usually used in signal integrity tools, but it can be used in simulation tools as well for EMC. The problem is less complex, so the equations are less complex and give you an answer quickly. But the key is it has to be small compared to a wavelength. It assumes that there's no propagation delay, which is not true, of course. But if you have parts that are very close together, much less than a wavelength, very small, then these LRC extraction tools are very useful. So the quasi-static simplified equations give you more efficient codes, so you get answers faster. That's really what it comes down to. They're usually written to complement a circuit modeling tool such as SPICE or something similar to that. But it has its disadvantages, like all the simulation tools do. It is important that you ensure the problem meets the criteria for a quasi-static solution. That is, all the dimensions must be electrically small because it's assumed that there's no propagation delay. And this is becoming very difficult with the frequencies of concern getting higher and higher and higher. For example, a 3-centimeter backplane high-speed connector is only, quasi-static is only accurate to about less than 5 gigahertz. So you can imagine at 3 millimeters that, it's going to be accurate only to 500 megahertz or so. So here's some examples of some quasi-static models that I've seen in the past. They're all connectors, and you can see how the parts are very close together. And at the frequencies that were being simulated, these were very small compared to wavelength. Now, there's a number of different modeling techniques: the finite difference time domain, the method of moments, the partial element equivalent circuit technique, transmission line method, and finite element method. And there are others, but they tend to be university graduate students' tools and don't get propagated out to people. I'm going to focus on the most popular ones, which is FDTD, the method of moment, and the finite element method. Now, the good news is you don't need a PhD to use them. You can get codes from many places. I say you can get them free from universities, but the buyer has to be aware, or the user has to be aware, because this was developed by a graduate student, and the primary goal of that graduate student was to graduate, and they're gone. And so there's probably no manual, or the manual is very weak. So you have to be very careful. You can purchase the software, of course, which is what most people do. But again, the user has to be careful to make sure that the simulation technique will do the kind of problems that they want. So I think that users need to understand the basic techniques and their limitations. So each technique has an area where it excels. Excuse me. And the areas where limitations. So oftentimes different modeling tasks are going to require different modeling techniques. Now, the Maxwell's equations, of course, come in two forms: integral, excuse me, I'm losing my voice here, integral equation methods and differential equation methods. The method of moments and the partial element equivalent circuit technique are integral equation methods. To find it out, excuse me a second. The finite element method, the finite difference time domain, and transmission line matrix method all use the differential version of Maxwell's equations. So a lot of tools will read a CAD file, and I'm very nervous about that because there's too much information. And so the models tend to become very large for a practical solution. So the human, the engineer, needs to decide what's important. Sometimes models can take days to run. If there's too much information, you might need something like a blue gene computer to, or some kind of supercomputer to run it, which is not practical for most of us. But the human needs to decide what's the most important and simplify the problem down to a reasonable size. You need to be careful about models that have too much detail. So here's a couple examples of a printed circuit board with two planes. The one on the right has a couple of differential traces, and they were read in from a CAD file, and then automatic gridding was applied. And you can see, just by looking at these figures, that there are many, many squares here, many, many cells. And each cell is an unknown and takes memory and calculation time. And so these are really impractical models to do full wave simulation on, just because they're too complicated. But when you look at it, you can probably simplify some of the things easily enough. The reference plane that's on the side of the differential traces has, I don't know what the right protrusions in it. That may or may not be important. You could always run two models with it one size, the larger size, and then the smaller size. And if it's not much different, then you've got a good answer. All right, the finite difference time domain technique is a simple technique. You have to grid up all of the space, and the fields are assumed to be constant over a cell. So imagine a room that you wanted to simulate something in the room. You would make all these little square boxes that fill up the room. Each box has to be denoted as air or metal or dielectric or some kind of magnetic material. And it's a time domain technique, which means that you get a wide band of frequencies all at once. And then you can get frequency domain just by doing an FFT. So Maxwell's equations in differential form look like this. We're not going to spend a lot of time on Maxwell's equations, but basically on the left-hand side, it's in one dimension, it's basically saying that there's a difference in the electric or the magnetic fields across a small area of space. By the way, when I say small, I always mean smaller than a wavelength. And for EMC purposes, 1/10 of a wavelength is usually good enough. And that basically that's equal to a time varying change in the electric or magnetic flux. The J term is conduction current. So in the air, we don't have any conduction current unless we have lightning or something. By the way, the minus sign that's on the lower equation means that the wave will propagate, and light is just an electromagnetic wave. So you can tell your significant other that without the minus sign in Maxwell's equations, you couldn't see anything because it would be dark. And they'll be quite convinced that you're a nerd. Well, we take the equation and we convert it to central difference. So basically the lower equation is saying at a certain time, the change in the field from one cell to another cell over the size of the cell is equal to the change in time of the magnetic field over the delta time. And of course, we have to put in the constants, in this case, mu, to make all the units come out right. And so here's the two equations for FDTD. And basically, it's just time stepping. So you've got a bunch of cells, and you go through and calculate the electric field for each cell. And each cell is, the electric field is based on the old electric field and the difference in the magnetic fields on either side of it. So coming back here, if I was to rearrange the lower equation, then looking at h at n plus 1, that's the new time. So I'm just going to say the old h, which is h superscript n, is going to be on the other side of the equation. And the E field is on the I's are changing, so that's position. So on either side of the cell we're calculating, we're finding the difference in the E field and the old H field, and that gives us the new H field. So this just says the same thing I just said. So in 2 dimensions, or 1 dimension rather, you can see the E fields are shown there, and the H fields are in between the E fields. They would normally be a cell, but I'm just showing a line here. And basically, you set a source, and the source then finds the H fields on either side of it, and the H fields on either side of it are going to be due to the old E field and a difference in the H fields, and so forth. And that just marches on. And so computers are really good at this, because this is really nothing more than accounting and counting. And So we find the E fields everywhere, then we go back and find the H fields everywhere, and then we're done. Eventually, we have to make time go on, and then when everything is done, then we're finally got the answer. A two-dimensional grid adds an extra E field in this case. So an H field, one of the dots, is equal to the old H field on either side of the old H field rather, and the difference in the E fields on either side of it, as well as above and below it. And you just go through and find the E fields everywhere, and then find the H fields everywhere, increment time, and go on. So for two-dimensional FDTD, you can use either two electric fields or two magnetic fields. And finally, the three-dimensional grid, which is what we really work with, the E fields are along the cell's axis, and the H fields are in the planes on there. And so if I wanted to find EX, for example, and the place it's highlighted in red, I'm going to take the old EX and the difference in the H fields on either side of it, and the difference in the HY fields on either side of it. And if I wanted to find HZ, it's going to be equal to the old HZ and the difference in EX on either side of it, and the difference in EY on either side of it. And again, we just march through, find all the EXs, then all the EYs, and all the EZs, and then all the HXs, HYs, and HZs. And then we do it again with time incremented. So we have to, as I said earlier, we have to assign each cell as either a perfect electrical conductor, some sort of metal, a dielectric, or a magnetic field. So we have to know epsilon, mu, and sigma. FDTD will give you outputs. Basically, they're perfect receive antennas. They receive both the E and the H fields from no matter what direction they're coming from. And the X, Y, and Z components are found individually as well. The nice thing about FDTD is that you can get animations. Since it's a time domain simulation, you can see how the fields are propagating through your model. And that gives you a lot of insight to whether or not the model's working right or not. We have to be able to stop the mesh at some point. And basically there are different kinds of techniques that allow us to find the fields at the boundaries. Most of them require far field conditions, so the impedance of the E and H fields are well known in the far field. Basically 120 pi or 377. So there's also something called the perfectly matched layer, which basically adds more cells. So if I have a computational domain that's, say, 100 cells by 100 cells by 100 cells, I'm going to add, for the perfectly matched layer, I'm going to add some number of cells. And I've heard numbers from vendors of 8 and 16. The more cells you do, the more accurate it is. And it works very similar to the absorbing material in an anechoic room. It basically has loss in these extra cells, and losses both in the E and the H field. So by the time it gets to the end, it it's all gone. I mentioned that the time step, the time step has to be small enough so the fields don't propagate faster than the speed of light. And that depends on the size of the cell. So typically, if we're in air, then the velocity is just the speed of light. But if we have some dielectric material or something, then the velocity is going to be lower. So basically, FDTD is a volume-based technique where all the domain has to be gridded up. You get a wide range of frequencies with one simulation. You find the E and the H fields everywhere, and it's very simple to learn and use. It's kind of a brute force approach. It's probably not very elegant, but it works really well. And when you're just starting out with modeling, oftentimes FDTD is the choice because it's so simple to use and simple to know when you're making a mistake. So it's very well suited to shielding problems with dielectrics and lossy materials, because we're, defining epsilon and mu. It allows infinite planes, so you can run a metal plane right up into the boundary condition, and there's no leakage around the field, the plane rather, sorry. It's not well suited to problems with long wires because I have to have a lot of what they call white cells around it for the boundary conditions to work properly. And it's very sensitive to resonances. So it's very good for shielding. It's not so good for long wires. Okay, the method of moments is next. We're going to break all the surfaces into electrically small patches, and the wires get broken into small segments. And basically, these small patches and segments are small compared to a wavelength. Again, 1/10 of a wavelength is usually good. Method of moments is a frequency domain technique, so you have to run the model for each harmonic frequency. Oftentimes, if you have a tool that does method of moments, it's going to allow you to set a start and stop frequency and a step size and frequency. And so you don't have to, literally go and run it for each frequency that you want. So basically, the current on every patch and segment is found due to all the currents on other patches and the source. And then the electric or magnetic fields are found at any point by summing the contribution of all currents. So an example here is a shielded box with some wires coming out of it, and the source is labeled there as common mode source, that we're driving one of the wires, and the little arrows denote the currents on the box and on the wires. And so the fields are going to be found by summing the contribution of all the different cells or patches to one observation point, and then you know what the answer is at that point. So there's basis functions. The assumption typically is that the pulse function, where the current on the patch or the cell is constant, can be different for the next one, but it's constant for that one. You can use linear, which you can see is triangular type thing. And on the right-hand side of the linear, you can see that it's a little bit better model of what the currents might be. But at each point where it changes slope, that's a discontinuity. And so it's not as accurate as reality. The piecewise sinusoidal is a bunch of sine waves that you put together, and now I've got a nice smoothly varying current. But of course, the more complicated the basis function is, the more it costs in time to calculate in memory. This just shows, the red shows the currents on different segments. Just happened, I just made these up. But there's also something called the impulse, where it assumes all the currents are in the center of the patch and there's nothing otherwise. It makes the calculation much easier, and they can go much faster, but it's less accurate. Okay, I kind of showed this already. I'm just showing the individuals. So as I said, the simplest basis function just needs one calculation per grid, but you need more grids per wavelength to correctly estimate the currents. The more complex basis functions require more calculations per grid, but less grids per wavelength. So it's a trade-off. Usually you don't get to pick. Usually the vendor has decided what they think is the best, and you have no choice but to go with what they have. So the method of moments is a surface-based technique, frequency domain. So the simulation has to be repeated for each harmonic frequency. The currents are found everywhere on all the patches and wire segments, and then the fields are found from those currents. It's very good for wire and surface structures, and it's simple to learn and use, just like FDTD. It's very well suited to problems with long wires because there's no white space required. It's even well suited to problems with large distances. If I wanted to use FDTD and do a simulation that goes out 10 meters, I've got to make all that area in between the receive antenna and the EUT as cells. So that's a lot of empty cells for nothing. So large distances is problematic with FDTD, but with the method of moments, it's just a simple equation that you put the distance into, and it's very straightforward. But it's not suited to problems with shielding or dielectrics or lossy materials. You can force it to do these things, but it's takes kind of an expert user. And finally, for the modeling techniques, the finite element method, again, it's a volume-based method, so all the space has to be divided to electrically small elements. You define the grid location as air, metal, dielectric. Usually they use triangular tetrahedral elements, and the fields are found in each element using variational techniques, which I'm not going to get into too much here. Just like the method of moments, it's a frequency domain technique, so that we have to run the model for each harmonic frequency we're interested in. But it's good for problems with irregular geometries or curved surfaces and so forth. It can handle different materials very well, and it results in what's called a sparse matrix, which can be solved very efficiently with efficient storage. So the method of moments creates a very full matrix. The finite element method creates a sparse matrix. So basically the way the FEM works is the entire volume is broken into small elements, as I said. The energy in each element is found due to the electric or magnetic field in an element. And then they take the first derivative of the sum of the energy in all the elements to find the minimum energy overall. And once you find that, you have the correct solution. And this is all done by the computer, of course. And then once you know what the currents are on each of the triangular cells, you can find the electric and magnetic fields. So this is just an example of a triangular mesh for an irregular surface. And a sparse matrix. You can see that the number of elements in the matrix is much lower than the method of moments, which is a full matrix. So FEM has an advantage over the method of moments for an equal number of unknowns, but usually you don't have an equal number of unknowns. You have a lot more unknowns for finite element method than you do for the method of moments. The mesh generation, you can't do that by hand. It's too complicated. But there are tools usually built into the Finite Element Simulation tool that does the meshing for you. And sometimes you can share the geometry with non-EM solvers, but I've yet to see that done successfully. So again, finite element method is a volume-based technique where the entire domain has to be meshed. It's frequency domain, so that means a single simulation for one frequency. Time domain finite element method is not widely available. I know it's at universities, and I heard that there was a vendor that was selling it, but I haven't seen it actually work. So it's very well suited to bound problems like waveguides, resonant cavities, and so forth, and very well suited to problems with large size differences within the model. For example, a microstrip that's only 10 mils above the ground plane, but you want to find the fields inside a box or something, and the 10 mils requires very small cells, but you can make them larger as long as they're still small compared to a wavelength. Just like FDTD is not well suited to problems with long wires, it's not well suited to problems with open boundaries. That's why I say it's good for bound problems like waveguides and cavities. There's been problems in the past with the absorbing boundary conditions, giving wrong errors. And so oftentimes you have to do two models, one with two with different size computational domains to make sure you're not getting an answer that's dependent on the boundary. Okay, and I could talk for 4 hours on model validation. It's something that most people don't do, and that's a mistake. There are 3 different levels of validation. Basically, does the modeling technique work? You know, finite difference time domain, does that work? Yes, it works. The second level is the vendor implementation. Did they do the coding right? Hopefully they've tested it, and hopefully they did it right. But the most important to an engineer is this specific model. How do you know you get the right answer? Just because the tool gave you an answer doesn't make it right. And so some other approach has to be done to validate the simulation. So if you have a very complicated model, it becomes very difficult to validate. You have to be careful about measurement comparison. If we're talking about an EMC semi-anechoic room, it could be plus or minus 7 dB because of the possible errors in the room itself, in the receiver, the antenna as it goes up and down the mast changes or can change by as much as 4 dB. So never trust a single model result. I have never done a simulation where I had one case that I modeled and said, "Eureka, this is it." If it's important enough to model, it's important enough to validate that model, and sometimes varying something, whether it's the length of a wire or the size of a box, or the size of the holes in the box, vary something to make sure that you're getting an answer that makes sense. Because the bottom line is that modeling does not replace the need for an engineer to have some knowledge of electromagnetics or at least RF. Now, I don't mean that you have to be able to solve Maxwell's equations by hand. I don't mean that at all. The computer's going to do that for you. But you need to know what to expect. And otherwise, you're just going to believe whatever it gives you, the simulation tool gives you, and it could be right. Well, actually, the simulation tool is probably right. It gave you an accurate answer to the question you asked it. Now, the question is, did you ask it the right question? If you've never, ever made a mistake in your life, then you can do away with validation. But I'll tell you what, I've learned more things by doing a model wrong than I have done by doing a model right. So you'd never trust just a single model result. And this isn't a religion, so it's not sufficient to simply believe that the result's correct. And the fact that you ran a simulation on some other model and you validated it doesn't guarantee the results from the new model. And as I said, garbage in gives you garbage out. You need to understand the physics of the problem and understand the limitations of the modeling technique and the software tools. So with measurements, you have to be very careful because of the EMC lab measurement accuracy. And as I said earlier, plus or minus 7 dB is probably about as good as you can really expect. Maybe a little bit better, but not much. So here's just a few things. You can see that the receiver is plus or minus 2 dB. The antenna factor variation for distance above the ground plane can be as much as 4 dB. The anechoic room is plus or minus 4 dB. And there's more, but these are the main factors. So where to go for more information? Well, there's lots of different websites. I have a few on the next slide, I think. There is a book, the EMC Computational Modeling Handbook. This is one that I was co-author on. And it covers different modeling techniques. It covers validation. And it covers the strengths and weaknesses of each technique. I think it's really important to understand that each technique has strengths, but each technique also has weaknesses. There's no one modeling tool that'll do everything. You can certainly go to conferences and learn. The IEEE EMC Society's conference always has a tutorial on modeling techniques, how they work, and so forth. Seminars such as this one. As I said, this topic and just a validation topic could be hours. To really cover the topic of modeling, it would actually take a day. There is an IEEE standard that talks about validation. So here's a couple of websites that you can go to. There are some practice models, if you will, on the different websites that you can if you see something that's similar to what you want to model, you can always challenge a potential vendor. Can you model this for me and show me that you have the right answer? I've seen that done successfully in the past. And there's a bunch of information that you can get from different websites here on the modeling techniques. I didn't cover the partial element equivalent circuit technique because that's not full wave 3D available commercially. And I didn't cover the transmission line method technique because it's very, very similar to finite difference time domain. So that's what I had to talk about today. And I'm happy to answer any questions. I see there's a couple of questions that came in.
Yep. As a matter of fact, so one question was, what are the typical price ranges, order of magnitude, the single user license for commercial simulations in industry consulting?
The most popular tools are on the order of $200,000.
There you go.
Yeah, it's very expensive.
Yeah.
There are some cheaper tools out there, and you know, some cases less than $10,000. It seems to me that if you buy a $200,000 tool and then you never get a chance to use it, I've had people tell me they can't do simulations even though they bought the tool because they're too busy in the lab fixing problems. And so it seems to me that if you buy a tool that is $200,000 and don't use it, that's rather career limiting.
So that actually begs a question. How reliable would open source EMI/EMC simulator programs be compared to available proprietary software?
I think that open source ones are perfectly fine. You got to do validation, and probably the options are not as many options. You know, for example, magnetic materials in finite element method or finite difference time domain probably are not available in open source. I'm really not familiar with open source tools, but
I think there's one NEC. They do like antenna modeling, just like an open source.
So NEC is a method of moments technique, and it's been validated many times by many people. So we know that the tool works. But again, you have to validate that you got the model right. One time I made a model that had a printed circuit board with a IC and a heatsink on it. And then there was a vertical printed circuit board right next to it. And I wanted to see how much shielding there was by this printed circuit board's ground plane to the other side of the circuit board. So I ran a model, and then I looked at the animation. It was an FDTD model. I looked at the animation, and the fields went right through my shield printed circuit board. I had, by mistake, I had made the circuit board out of air instead of metal. And, you know, and I tell people, quite honestly, if I can make mistakes, so can everybody else. And I have made many mistakes, but I've always validated my answers that I had the right model. And even with the NEC, you got to make sure that you've modeled correctly the thing you're trying to simulate.
So since you covered the three different simulation modeling, the types, the modes, should folks always consider kind of doing all three of those for validation accuracy?
I think that, well, first of all, I doubt anybody can afford all three of them. But as you pointed out, NEC is free. And quite honestly, my go-to simulation tool is in finite difference time domain. There's too many gotchas with finite element method for me, anyway. You have to be super careful. You have to be kind of an expert in finite element method. And even though one of the most popular tools is finite element method, you have to be awfully careful about it.
Okay. I'm looking to see, most folks would like to know if your presentation would be made available as a PDF for folks
Sure.
to refer back to.
Yeah, is that something you can post somewhere?
Sure, I'm happy to do so.
Okay, I'll send you a PDF file.
All right, perfect. So I'm looking to see if there's any other questions. I don't see any coming in. I guess, well, we're pretty much at the top of the hour here. So again, just a reminder, like if anybody has a question after the webinar, just feel free to send your questions in. You can send them to questions@wll.com. And someone from our team, will contact you with an answer. So I guess we'll go ahead and wrap this up. Thanks again, Dr. Bruce Archambault, for taking time out to enlighten us about what to know before you buy EMC Simulation Software. So on behalf of Washington Laboratories Academy, we'd like to thank you all for your attendance, and I will go ahead and close out the event.
Okay, thank you everyone for attending.
All righty, everyone, please enjoy the rest of your day and be safe out there. Okay, bye-bye.
Bye now.